Just an explanation on how to complete the second technology assignment. So that would be Tech Assignment B, Modeling Polynomials. So I'll open that file. So you see the objective to use online software to model and analyze real world data. So we have some information here. We're going to put this into a table in Desmos. All right, and then from there we're going to create some polynomials and then use that to draw some conclusions. All right, so I'm going to open a Desmos calculator, desmos.com. If you don't have an account, create one and then sign in. Click on Graph and Calculator. If you want to put a table of data in, you would hit that little plus icon and select Table. Now, our data points go from 0 to 14 by even numbers. So 0 to, once Desmos realizes that there's a trend in the data that you're plugging in, it will autofill. All you have to do is keep hitting enter. All right. Not so lucky when it comes to the other data points. So 94, 82.9. It's not seeing any kind of reasonable trend here, so it's just assuming that we're putting in raw data. So 73.6, 65.7. Uh, 49, 53.3. Oops. And 48.5 and 44.4. All right. So we have some data points in. Nothing shows up on the graph here because this is only going from negative 10 to 10, and these y values are going from, well, the lowest one I see here is 44.4. The highest one is 94. Right. So if I click on this little wrench here, graph settings, I can change my y-axis to, instead of going from negative 5-ish to 10-ish, I can make it go from negative 5-ish to like 100. And now you see the data points. All right. So what we're going to do here is put in these different models. All right. Y1 tilde a plus b x1. All right. You could try to do a little copy paste, but I'll show you what happens when you do that. That, among other things, right? Because it's different software, you know, different rules for different software. So we just have to type it in manually. So y, if you want a subscript of 1, for whatever reason, Desmos knows that if you put a number adjacent to a letter, you're probably trying to do it as a subscript. So that's nice. We'll take advantage of that. Tilde a plus bx1. All right. So what it'll do is it'll fit a line to these data points. This r squared value, that's called the coefficient of determination. We're looking for the one that's closest to 1 when we put in the different models here. All right, so we got all these different possibilities. We're looking for the instance in which the r squared value is equal to 1, if at all. You know, so the next one is y1 tilde ax1 squared, right arrow to get out of the power. The keyboard shortcut for a power is shift 6, so it's the caret symbol. So shift 6 makes an exponent. All right, so plus bx1 caret, I don't actually, apologies for that, I don't want a power there. It's just bx1. Right arrow plus c. Now I have a parabola. You can see my r squared value. It goes back and forth between lowercase r squared and capital R squared. There's a reason for that. It's just more of a statistical conversation rather than a function calculus, precalculus conversation. So different story for a different time. But they are an apples to apples comparison. So 0.97 is closer to 1 than 0.915. So turn this one on, keep this one. All right. So we'll try a cubic. y1 tilde ax1 cubed plus bx1 squared plus cx1 plus d. All right, so power of 3, 2, 1, and then power of 0. You can see that this one, it's ever so slightly better. Not much better, but it's a little bit better. All right, so I'll keep them both on because it's an old expression that I like to use. I call it, I mean, it's a baseball reference. It's the tie goes to the runner, but that doesn't always land. But basically what it means is that if you have two r squared values that are close, very close to one another for two different functions, you default to the simpler function, all right, the one that's easier to work with. So these two are very close to one another. I would go with the quadratic because that's an easier function to work with. But let's see about the quartic. y1 tilde ax1 caret 4 plus bx1 caret 3 plus cx1 caret 2. By the way, if you haven't appreciated the importance of saving your work on this, after you type this one in, you will. So plus dx1. All right, now the tendency is to say, all right, now I'll add an e, and that may be okay, but if you look at the constant, if you look at a comparison between or among all these different functions that we put in, see, every time I put in a coefficient ab, it gave a parameter ab. abc, it gave an abc. abcd, it gave abcd. But this time I put in abcde, it gave me only a, b, c, and d. That's because e is already a constant, 2.718. So we actually can't use e, so we skip over that one. All right. So if you look at the assignment here, we skip over that and we go right to g. All right. Now, before you're like, well, you don't know the alphabet. Well, we also skip over f because f is usually designated as a function, all right, f of x. So we skip right to g, and you see now it gives us a g value. All right. Now, when we perform a comparison here, we see 9701, 9706, 976, which is better than these other two. All right. And it even looks visually like a better fit. So we would keep going. Now we would try the quintic. Ax to the fifth. Ax1 to the fifth. Those subscripts are necessary because the data points are in columns x1, y1, and if we're using a regression model, it's relating those columns of data to one another. All right, so b x1 to the fourth plus c x1 to the third plus dx1 to the second plus skip e, skip f, g x1 plus h. And just make sure you have a coefficient for each one of these, or actual value for each one of these coefficients. All right. Now, 0.9806 is better than 0.976. It's a question of how much better. It all depends on what your perspective is. All right. So we have the best fit model. All right. Now you may look at it and say 0.9806 isn't really that much better than 0.9701, so I'd rather use the quadratic. Or you might even look at it and say the context of the situation. I mean, if you're talking about a projectile being thrown up in the air, you know, you throw a ball up in the air, gravity captures it and pulls it right back down. That's in the shape of a parabola. You'd say, well, yeah, mathematically this is a better model, but physically, or you know, in the context of the situation, a parabola is a better fit. Then you can make that judgment. All right. But in the absence of that information, this is what I'm going to go with. So what I would then do is take all this information here, copy paste, but instead of y1, I'm going to make it f of x. That's why we hung on to the f. I'm going to get rid of all these little subscripts. You're like, why did we put them in to begin with? Well, we needed to put them in order to regress the model, to come up with a regression equation. But now that we have that, I just want it to be a regular function so that I can perform computations. All right, now it looks like it's not taking my adjustment, so there might be a matter of an extra value here somewhere that I didn't take into account. I might have to retype it in. All right, as annoying as that is, that's what I'm going to do. So f of x is equal to ax to the fifth plus bx to the fourth plus cx to the third plus dx plus g a, b, c, d. I missed the power of 2 plus h. All right. So we're good there. I have my function in. Now we have, because there's a disagreement, we've used the a value repeatedly. What I would do is I would save this as tech b precalc, something as kind of like a placeholder title. So now that I have it, what I would do is I'd just wipe out all the stuff that I don't need. And you'll see that now there's no disagreement between the a values and the b values. It's not overused. I now have a function that I can use. All right, so I can turn them all off, turn them both back on. The benefit of this version in comparison to this one is I can do math to this one. All right. So when it says something like use the best fit model to evaluate the function at x equals 1, f of 1. That's all it's really asking. Now there is some context here, so I'd like to think about what this represents. T represents minutes, time in minutes. All right, and so that's the lowercase t. And then the result of that is temperature. So the x and the y, based off of what we just typed into Desmos, would be time and temperature. All right, so what this is telling us is, open quotes, after 1 minute, the temperature is about, a little rounding is okay because we got the full-blown decimal right there, 88 degrees Fahrenheit. Here we go. H-E-I-T. That would have been nice. How do you spell it? Well, I'll look it up in a minute. But that would be the interpretation there. So that's nice. Then the next part of the process, or problem I should say, is to find when the temperature is at a minimum. All right. So I just Googled the spelling of Fahrenheit. F-A-H-R-E-N. Is it really this simple? Yeah. Look at that. All because I didn't capitalize it. Anyway, when the temperature is at a minimum. Well, this is time, and this is temperature. Or the y-axis references temperature. I can put these labels in just so I don't lose track of it. Time, temp. Minimum temperature. Well, it goes down forever. This is a polynomial function. However, I don't expect contextually a bun taken out of the oven to reach a temperature of negative 20 degrees Fahrenheit, or even 0 degrees Fahrenheit, or even 32 degrees Fahrenheit. These are some things, room temperature is probably the lowest it'll ever get contextually, all right? But when it says based off of the model, in this case, using the best fit model, find when the temperature is at a minimum, it would be at infinity. Okay? So temperature, oops, you got to use open quotes here. Temp is at a minimum. And you could zoom out to get a sense of the graph, but this is a fifth degree polynomial, so its behavior is positive infinity to the left, negative infinity to the right. In this case, temperature is at a minimum when time is positive infinity. All right, that's based off of the model. That's what they were asking us for, so that's how we answer it. All right, when is the temperature at a maximum? Well, it doesn't look like there's ever an absolute maximum. We have a little relative maximum here, a little spike in the temperature, but that's not what they asked. The temperature is at a maximum back the other way. So if we follow the path in this direction, the temperature is at a maximum. I keep forgetting, open quotes, when time is at negative infinity. All right. So contextually, this model doesn't really work very well for us because we're going with a function that's infinite in nature. But if we truncate it, if we were to say, and this is beyond the scope of what the assignment is asking us to do, but it just kind of giving you the information here, if I were to truncate it and start the graph off at this location and end it at this location, then you'd have more of a reasonable window into what's going on. And in fact, you might even cut it off at, let's see here, maybe around right here, because now you're looking at room temperature roughly. All right, so you may be looking at maybe from 0 to 6 minutes. So if I'll just show you really quickly. It's not something you would need to do, but just so you get a little bit of an understanding of it. If I say 0 is less than or equal to x, which is less than or equal to 6, and only focus on this part of the graph, this actually might be more meaningful for us. All right, and that's because once it gets to room temperature, you probably don't care about it anymore, or at least this function. All right, but like I said, that's beyond the scope of the assignment. All right, so once you complete this, then, well, I'll just show you. You're going to do that with a fresh set of data. This is talking about distance of a spherobolt, which is a robot if you don't know, for changes in time. All right, so you're going to do this process for this data, but then you're also going to collect real data that can be organized in a similar fashion to this. Apologies for the formatting there, I'll fix that. And then answer basically the same questions. All right, so you're going to create, I would recommend that you create two separate Desmos links, one for this problem and one for this problem. All right, and that's your tech assignment.